before that, Dr. Nirmala, she will be the chairing the session. So she will introduce you to the audience, and then later you can share the screen.
Sure.
Yeah, you can start.
Announcement.
It's a wrong slide. It's a wrong slide.
Yeah, sorry.
Hello, sir. Good evening, sir.
Good evening.
So it's my honor to introduce the next speaker of this session, Dr. A.M. Kannan. Dr. A.M. Kannan is a professor in the Polytechnic School of the Ira A. Fulton Schools of Engineering at Arizona State University, USA. He is specialized in low temperature fuel cells, solar cells, and large scale energy storage in batteries. He was visiting professor at Tampere University of Technology, Finland, principal scientist at the VTT Technical Research Center of Finland. He possesses strong academic and professional experience, having also worked as chief scientist at Hoku Scientific Incorporation, Hawaii. Dr. Kannan has published extensively and presents regularly at international conferences on batteries and fuel cells. He serves as an associate editor of the International Journal of Hydrogen Energy, as well as on other editorial boards. Now I request Dr. A.M. Kannan to deliver his lecture.
Still
you can share his screen. Yes, sir, it's visible.
Okay, all right. Yeah, thank you for the nice introduction. So I know it's a night in India, so I see that there are hundreds of participants in the VCAN conference. Thank you, Dr. Nirmala, for inviting me for the conference. So I'm going to give a quick overview of what we have been doing recently on solid electrolytes for lithium-ion batteries. So to have a very quick run through of the history. So let me see if I can get. Okay. So if you look at this screen, I mean, the lithium-ion batteries all started in the late 80s, and from 90 onwards, when this, Sony Corporation introduced carbonaceous anodes. Then in 92, in fact, there was solid electrolyte based on oxynitriles. And then probably after like 10 years or so, there was electrolyte which is kind of based on maybe 90, yeah, probably by 97. And it was mostly fast ion conductors similar to the Nasicon, so the Lisicon electrolytes. And then in 2007 was the time when Professor Murugan, so he was in Germany as a postdoc, introduced the Garnet type electrolytes. Then by almost 10 years, so the progress had been relatively slow on the electrolyte development, mainly the solid electrolyte development. And only after 2015, there were a few research organizations and also companies trying to introduce, on an experimental level, all solid state batteries. So as you see here in 2018, so you could see that lithium metal was used as an anode instead of carbon electrode, and then lithium lanthanum zirconium oxide, that's Garnet structure, and obviously LLZTO cathode. So as you see, this is a structure with all solid state lithium metal batteries. So that was one of the major probably happening in the electrolyte development. And the whole thing is mainly for reaching 500 watt-hour per kilogram energy density. I don't know, I think bottom is not visible here, but so the goal is to actually reach 500 watt-hour per kilogram as a energy density, mainly for having a longer driving range per charge for in the electric vehicle, and that's also actually being supported heavily by the US DOA's battery 500 consortium. And in fact, the motivation comes for the development of solid-state batteries comes from the challenges and issues associated with the currently available lithium-ion batteries. So you can see, automobile going into flame. So mainly because of the fact that the solvent is an organic solvent with relatively lower flash point. So, mostly safety aspect. And the liquid electrolytes also need a separator, which is, typically polymer membrane or, maybe like, 20-25 micron thick separator that could allow lithium to grow into a needle shape to physically short between the anode and cathode if you have to use a lithium. So the major breakthrough is mainly with a solid electrolyte, if it really happens probably in the next decade or so. So solid electrolyte being, one component which would act as an electrolyte and also separator. And this material being highly impervious to any material movement through that, excepting ionic movement of lithium, could lead to extremely higher level of safety. And certainly, because of the extremely low or very fine pore structure or absolutely no pore, it could also prevent dendrite growth. So in that way, we could use lithium metal as an anode in the rechargeable lithium batteries with a solid electrolyte. That will make the batteries extremely energy dense. So that's because of the extremely higher electrochemical equivalence of lithium. And in fact, all the solids are, mostly solid electrolytes. That could be used as a bipolar materials on, anode and cathode. So this could become almost similar to the way the proton exchange membrane fuel cells are being fabricated. So, that's a possibility that the electrode can be bipolar. And in fact, we hear on and off that Japanese automobile companies are mainly aiming towards all solid-state batteries by 2023. So that might happen, or it may little bit get pushed up. But you can also probably you would have seen in the past couple of weeks that Tesla and also CATL in China has been publicizing their 1.24 million miles lithium-ion batteries, and they also say that the battery could survive for 16 years in the automobile. So that may be again, one of the motivational factors to still, focus heavily on the solid-state batteries to also improve. In addition to the safety, you can also improve the energy density and also power density. Probably is a question as of now because of the relatively lower lithium-ion conductivity compared to that with the liquid electrolytes. So this slide gives you an idea about where the market is going towards. So you can see at the left end, it is the currently available lithium-ion batteries with a liquid electrolyte. You can also see a separator. So again, the anode is on the right-hand side with the graphite and also the left-hand side with the cathode, which would allow the intercalation of lithium back and forth during charging and discharge. So if the separator and liquid electrolyte is replaced by a solid-state electrolyte, then there's no separate membrane or a separator, but just a single sheet. So that could physically separate and also ionically conducting lithium between anode and cathode during charging and discharging. And the bulky graphite electrode can be replaced if you can, optimize the solid-state electrolyte, by the lithium metal. So that would again, certainly improve the energy density. So with that, if you just retain the lithium metal anode and also the electrolyte, you could actually replace the LCO or any other cathode material by sulfur electrode. So this could become a lithium sulfur batteries with a solid-state electrolyte. or it could be with a air electrode on as a cathode and also solid state electrolyte and a lithium metal. So there is a possibility that this solid electrolyte could lead to advanced lithium sulfur batteries with absolutely solid materials and also lithium air. So lithium having extremely high electrochemical equivalence, 6.94 ampere hour per gram, and also air electrode with unlimited amount of active materials of oxygen from the atmospheric air. So this could actually lead to closer to or above, well above 1,000 watt-hour per kilogram if it becomes frozen with time. So that's a huge potential for these solid-state batteries in terms of energy density and also extremely high level of safety. Solid electrolytes, obviously, like any other product, solid oxides also come with a lot of challenges that actually opens up a lot of research opportunities for researchers around the world. So the ionic conductivities are relatively lower compared to that with liquid-based electrolytes, and that is mainly true when the temperature is on the lower side, so in temperature and the sub-zero temperatures. And one of the major issue is the larger interfacial resistance, because you have the solid electrodes, anode and cathode, and also solid sheet of electrolyte. So when things are put together, it also leads to huge interfacial resistance. So that's again, one of the major focus area in many research laboratories around the world. That all, in addition to the interfacial resistance, solid electrolytes could also lead to electrochemical compatibility. Even though the solid electrolytes can have a huge electrochemical stability window, but it could also lead to compatibility with lithium anodes and other high voltage cathode materials. And in addition, there could be some stress associated with this, physical stability of these electrolyte or electrode electrolyte interface. If they degrade, this could also lead to stress and then also maybe breaking up or decreasing the integrity of the electrode electrolyte structure in the all solid state batteries. As I have highlighted in red, so interfacial resistance is one of the major issues. But again, researchers have been able to come up with the strategies. So if the interfacial resistance can be handled with 4 different approaches in terms of improving the compatibility or to improve the contact area of the solid state electrolyte with the electrode, and also to handle the interfacial stress variation can be somehow manipulated, and also to have improved mutual diffusion of the lithium ions. So the strategies in handling the incompatibility is also by using buffer layer coating. So it could have between anode and cathode, you can have a lithium niobium oxide or lithium phosphorus sulfide. So there are many possibilities. That's actually sulfur electrodes. And in other words, you can have an artificial ACI layer, solid electrolyte layer. And in terms of improving the contact area, so you can have a nanocomposite electrode with multiple components in terms of somehow modifying the interfacial structure with the nanocomposites. And again, you can have a alloy. So instead of just a lithium metal as an anode, so you can have a lithium metal anode, and then at the interface you can have a lithium metal alloy. So mainly, some kind of a functional variations or gradation in terms of not exactly with just three components, but you try to somehow soften the surface with some kind of an alloy, so that the structure becomes stable and also improves the surface area. You can see that it's not a straight line, right? So you can have a corrugated structure or any other configuration to have an improved surface area. And in terms of reducing the stress variations, you can have multiple components, including RGOs also. And also it says, flowable PEG electrolyte. So that's again, polymer, but so you can have a extremely thin layer of other materials to make the surface a little more flexible. So that way, I mean, you have the functional materials of all solid state components, anode, electrolyte, cathode, but in terms of improving or, reducing the stress or improving the structural stability, you could have components which are well known in the literature and very well understood, like, RGOs and PEGs. And also have particle coatings. So in terms of improving the diffusion or, having a longevity of the electrodes, you can have the electrode particles and, coated with electrolyte as the electrolyte or as the electrodes become closer to the electrolyte structure. So in terms of, again, functional gradation in terms of improving performance, durability. So cost probably is, again, is not being looked at very carefully, but, as of now, it's probably on the higher side because these materials cannot be co-sintered or the process is not available as yet. But again, there are opportunities to integrate all these materials to have extremely high performance with, wonderful safety feature, along with maybe reduced cost once the batteries are being made in volumes. So solid electrolytes, mostly come from polymer electrolyte, as I just mentioned. In the solid polymer electrolytes, you can have a PO, PAN, or PMMA, or PVDF with salts, lithium salts like perchlorate or hexafluorophosphide salt that can have good ionic lithium-ion conductivity, again, compared to solid electrolytes with inorganic materials. But in addition, because it's a polymer, so it can also lead to a little bit of flexibility, and certainly the density is lower for these polymers, so you can have a lightweight material. And because these are polymers, so you can have a better processability, and certainly these materials can also lead to slightly lower cost also. But, because these solid polymer electrolytes also have cationic lithium and also anionic component. So that actually leads to relatively lower lithium ion transference number. So most of the literature talk about less than 0.7. One of the reasons one says they could actually increase the transference number of lithium ion all the way up to 90%, but still again, it's not 100% ionically conducting. So that's one of the major disadvantages with the solid polymer electrolytes. The other electrolytes, certainly, inorganic materials comprising sulfide glasses or garnet structure or perovskite, or also silicon structure. So, mostly the major categories involved are comprise sulfides and also oxide-based solid electrolytes, which are being heavily focused on these days. So sulfide electrolytes, again, the commonly used ones are sulfide and glass materials like lithium sulfide, phosphorus sulfide, or lithium sulfide, germanium sulfide, or lithium sulfide, bismuth sulfide, or silicon sulfide. So all these materials would lead to conductivities up to 10⁻⁴ or 0.1 millisiemens per centimeter. And you can also have a combination of modified silicon with a sulfide, because these are the sulfide materials, and that could actually show higher conductivity of probably 2 to 3 orders of magnitude compared to other materials. And that is mainly because of the relatively larger ionic size or higher ionic radius of the sulfides compared to oxides. That would actually open up the larger transport channels. So lithium ions can easily go through the structure to have higher conductivity. But sulfides have sulfides are relatively cheaper too compared to other materials, but again they have some issues. So one of the materials very recently reported is the chlorine doped silicon sulfide. You can see the structure here, the formula. So that material showed almost 2.5 × 10⁻²⁶ per centimeter. That's relatively higher. But these sulfide materials are very, very sensitive to moisture. So when the material gets into contact with the moisture, they can convert the surface into hydrogen sulfide, and that probably the major impact which limits their commercial application as of now. But this doesn't mean that the sulfide materials are not going to see the end of the tunnel, but this is one of the major issues right now. So the next one is obviously the garnet type oxide. So it was in 2003 when Dr. Tamilnadu, so who is in Calgary right now, and so he reported garnet-like structure, which is again based on lithium lanthanum, niobium, or tantalum-based oxides. So that was one of the very good materials reported 17 years ago, and then in 2007, Dr. Murugan, who is in Pondicherry University now. So that material was lithium lanthanum zirconium oxide. That was probably the one opened the door for research on this garnet structure for lithium and battery solid-state electrolyte. So that material, when reported, it was again up to 10⁻³ times 3 and 10⁻⁴ per centimeter at room temperature. So this material garnet structure, so mainly the lithium lanthanum zirconium oxide, can actually stabilize in two different configurations. So cubic phase and also tetragonal. The tetragonal structure has a very stable structure and could also show almost 2 times the conductivity compared to that tetragonal. So that means synthesis is a major problem to have stable cubic phase. But there are multiple studies with hundreds and hundreds of publications on these materials as of now, with dopants ranging from tantalum to tellurium, and that is actually known to stabilize the structure in cubic phase. But again, there are reports that this material can also become less stable if it is exposed for longer duration to moisture, where lithium can actually change with protons. So again, many researchers still question the stability of these materials, thinking, oh, we think it's a lithium conducting garnet structure, but because of the instability in moisture, can it become a proton conductor? So if that happens, the battery is not going to work with the lithium. So this is again, very important feature, that the structure has to be very stable with appropriate synthesis method to have this relatively metastable cubic lithium lanthanum zirconium structure. So this material certainly has a relatively high lithium ion conductivity along with a wider electrochemical window. So that means this material has the potential to be combined with the high voltage or 5 volt cathode materials to also have a target of higher kilogram or energy density. Okay. So this is exactly we did. So I have a few slides to show our recent results on tantalum doped garnet structure. So again, we already know that this material is known to show higher conductivity and also high robustness. So stability with solid electrodes is also known to be better. So what we did was actually, synthesizing these materials by 2 different methods to identify which one is going to be more commercially viable, and also try to use different medium or different crucibles for sintering them to have a stable structure. So one method is a traditional solid-state reaction-based one, another one is a molten salt. So in the solid-state reaction, again, the material could lead to more agglomerates requiring, longer, highly intense ball milling process. So you start with the precursors, mostly oxides and some lithium sulfides. So the molar volume and also with a slightly higher lithium hydroxide to have compensation for the loss of lithium during the process. So the material prepared is again, lead to relatively larger agglomerates that needs, longer ball milling. So to have, finer particles, and then, so initial calcination would give a stable structure, whether it is, tetragonal or cubic, but the goal is always to get to cubic. But at the same time, what is important is to make the pellet, which is highly denser. So the density, relative density should be at least more than 95% to have absolutely no growth of dendrite if the electrolyte pellet is subject or fabricated into a full cell, whether it is lithium or with lithium metal, and also the LCO cathode or other cathode materials. So if the particle size, you might ask, if the particle size is larger, what happens, right? So if the particle size is larger when it is made, after we make the pellet and then densify, the pellet cannot lead to higher density of above 95%. So that means, suddenly the particles have to be broken into relatively finer form to have required pellet densities. So this is again, it's a similar, but again, this is a one-part method. So you can have the salt, which is a medium, which is, lithium chloride and potassium chloride salt. So that's a medium. So that melts when the temperature of the precursors go to 900 degrees Celsius. So the reactions happen. So with all the precursors in liquid form or liquid medium. So that's a major advantage. And then, once it is taken out, you can disintegrate, or you can actually wash it thoroughly with water. So that washing has to be carefully done to avoid or eliminate lithium exchange with the proton. So once that is done, then you have actually relatively smaller particles, and then you can have a very quick or shorter milling process to have a relatively finer and then make pellets. And once you sinter, the pellets always lead to almost kind of semi-transparent with the extremely high dense and also non-porous structure. So the variations we did was after these pellets were made, we had different methods. So, after ensuring that the pellets have a stable cubic structure, so obviously both the methods, salt-state reaction and also the molten salt method, led to cubic Garnet phase. So once that is done, the surface are mainly to understand the particle size and then also the distribution. I don't think, you can see the value here, but I think the diameter at 50%, 90%, so the particle sizes are relatively larger for the solid-state reaction base. But in the molten salt, the particles had a kind of a bimodal or even trimodal distribution before milling, but after milling, almost it had become only few percent of larger particles and relatively smaller for the molten salt method. Then the powdered materials were made into pellet, so that was about 10 millimeter diameter. And the sintering is a major process step in making the pellet highly dense. So we had three different approaches. One is to sinter the pellet in platinum crucible, and another variant is to have the pellet sintering in the alumina crucible, and also the another one sintering in alumina crucible, but also by adding sintering aid. So sintering aid is mainly to improve the density, and all these pellets were actually covered with a mother powder to avoid lithium loss during the densification process. So this table also gives you the lattice parameter. So as you can see, all these three different types of pellets from the powder made by the salt-state reaction, and also similar one with a molten salt method. So sintered in platinum crucible, sintered in alumina crucible, without any additive, and also alumina crucible along with the 1 weight percent gamma alumina as a sintering aid. So if you see that pellets sintered in platinum crucibles, both the pellets led to lattice parameters almost the same, 12.91. So it's certainly cubic phase and no other impurity phases. And the relative density was actually, well above 95%, probably, very well qualifies for to be made into full cell activity. Ionic conductivity, lithium ion conductivity is about 0.5 and 0.6. So again, very what has been reported in the literature. So compared to, relatively lower density for the pellets. So the reason why we added alumina is mainly to ensure that density is, improved. So that has been done, documented very well in the literature. But we actually saw it on completely off, because with the alumina oxide or LTO3 as a sintering additive, sintering aid, the density values were lower and the conductivities were also lower. So that was mainly due to some grain growth and things like that, or formation of some unwanted impurities like lithium aluminum oxide in the grain boundaries. So you can see that the pellets, so SSR-A, that's in platinum crucible, that's in alumina crucible, that was in alumina crucible with the aluminum oxide as a sintering additive. So with the solid-state reaction-based powders, so these pellets showed, absolutely no impurities, very clear single phase. But in the molten salt, when the material was actually sintered, or pellet was sintered along with the alumina LTO3 as a sintering aid, we had obtained also some impurities like lithium aluminum oxide. So that could probably is going to lead to lower ionic conductivity. Whereas with the platinum, without any alumina. So in this case, when you have alumina crucible, it has been reported that the aluminum can actually diffuse from alumina crucible. So because of the extremely high temperature, almost at 1200 degrees Celsius. And the ICP analysis was actually carried out to ensure that the required or the expected composition was obtained. And the cross-section again is very important, right? So like I said in the beginning, so one of the important feature or characteristics required for the solid electrolyte is also to have, almost pore-free cross-section. So you can see that the ones on the left-hand side, so pellets are made are sintered in the platinum crucible for both. The powders made by solid-state reaction and also the molten salt method. So the one here for the alumina crucible, and the one our dog. So the one on the right-hand side, you can see that there are more pores for both the pellets. In fact, the pellets sintered sintered in alumina crucible with the aluminum oxide as sintering aid for the powder made by the solid-state reactor. You can actually have some kind of a crack and also a larger opening inside the pellets. So relatively more pores in the grains, mainly because of the aluminum oxide as a sintering aid. This was to make sure that aluminum is actually there everywhere for the pellets sintered in alumina crucible. So you can see this here in the B, and also for the C. That's because of have alumina crucible along with the alumina powder also as a sintering aid. Okay, so aluminum actually gets distributed throughout the grain for both the solid-state reaction-based and also molten carbonate-based powders. So this certainly, has a correlation with compositional verification carried out by ICP. That's a lower amount of lithium, or aluminum occupying the lithium sites. So this one you can see that the larger grain growth. So this is, this is just, we think, this is how it is, right? So without any core or without any aluminum. So for the pellets made in platinum crucible, this is the alumina crucible and with aluminum additive. So the connectivity values were again, here. So certainly, the pellets is sintered in the alumina crucibles, and also along with alumina as additive led to non-uniform grains with larger pore sizes, okay? And the densities were lower than 94%. So all these pellets were, I don't know how many times, but certainly 4 or 5 times reproducible way. So all these materials were highly reliable. And the results or the manuscripts actually in under revision in the ACS advanced interface. So in order to understand the connectivity and also the conduction mechanism, impedance measurements were carried out at various temperatures, including that at minus 60 degrees Celsius all the way up to room 25 degrees Celsius. That was done mainly to understand the Arrhenius behavior and also to estimate the activation energies. Okay. So the total connectivity certainly comes from both bulk and also the grain boundaries. So this is for the pellets made by the solid reaction and also the molten salt. So you can see, we also did the little bit of line fitting. So you can see that the semicircle in the higher frequency region is mainly due to the relaxation taking place in the bulk. Okay. So certainly, the pellets sintered in platinum crucible showed lower resistivity, compared to those with the aluminum crucibles. So here we can see the parameters estimated from the impedance patterns. So both the resistivity and the connectivity, that's actually the total. And activation energies. So the pellets sintered in platinum crucible showed around 0.38 EV as activation energies. So you can see they are in this plot. So the values again, are labeled here, but I think it's mainly because of the aluminum, which is getting into the grain boundaries. So density and also the conductivity values were given here. So some, with the multiple densification process, in graphite electrolyte, I think in 2016, Yamada et al. Reported 0.69, but we reported only, or we could get only up to 0.5 by the solid reaction, and also around 0.6 with the molten salt. And there are also different methods with co-precipitation. That one actually showed the highest connectivity as of now. But again, still, studies with full cell, but we were able to fabricate symmetric cell with a lithium mainly to understand the break-in current, so which are actually in the making right now. So I don't have the results to show you. So coming to an end, we were able to actually at least get reproducible pellets with relatively higher density, and also the connectivity is all the way up to 0.6 millisiemens per centimeter using 2 different methods, so molten salt and also the salt-state reaction. So molten salt method is a relatively simple method, but I don't know how easy it is to scale up, because there are steps which are conducted in a controlled manner to wash the salt, lithium and sodium, lithium and potassium chloride salt. So, aluminum, coming from alumina crucible, if the crucible is alumina, or like any other studies, if you use alumina powder as a sintering aid, aluminum can easily diffuse into the bulk, which would, certainly occupy the lithium site. So that means, lithium ion conductivity is going to be lower. So one has to be really careful. Okay? And also when we use sintering aid, so that could actually lead to formation of different garnet phases along with the lithium aluminum oxide impurity. And that could actually get into the grain boundaries region. And again, that would lead to lower connectivity because the connectivity comes from both the bulk and also the surface and also the grain boundaries. Okay? So certainly the molten salt method can also be an alternative method for making or synthesizing lithium, lanthanum, zirconium, tantalum, oxide with higher connectivity. So at the end, I would like to acknowledge the graduate student Pawan and Dr. Candace at the ASU and Dr. Mo. So we had multiple times a discussion, and so our low temperature impedance measurements at minus 60 degrees were all carried out. Thank you very much.
Thank you, Professor Kannan. I have a couple of questions raised by the audience. Can mesoporous carbon be helpful in controlling lithium dendrite growth in lithium metal batteries?
So as long as the pore can be blocked, if the sintered pellet can have higher relative density, you can avoid the dendrite. There's no way, electrochemically in the batteries, you can limit the lithium dendrite growth. So one specific thing is like, putting a wall. So that to, impervious wall to avoid. So any material which would aid or which would help in sintering the pellet well without any pore structure can be used.
Yeah, thank you. One more question. The type of solid electrolyte that you would prefer for good energy density in supercapacitor application?
So lithium, this lithium conducting material can be very easily used in every application where you need, lithium conduction. But again, it's very important that as long as you do not have material incompatibility, you can use these electrolytes. So whether it is, in like I said, the lithium all solid state lithium ion batteries, they can also lead to all solid state lithium sulfur batteries, all solid state lithium air batteries. So that means, it could also be extended to capacitors or supercapacitors or capacitors.
Yeah, last question, sir. How to synthesize amine-derived pillared graphene hydrogel for solid electrolyte-based hybrid supercapacitor?
I think I'll pass it to the item. I have no idea.
Okay, sir. Thank you. Thank you so much for your extensive lecture. And also thank you for accepting our invitation.
Thank you very much.
Thank you, Dr. Kannan.
Yeah, thank you.
Dear participants, there's a small announcement in tomorrow's schedule. The talk by Dr. Challen Venkatachalam from University of Lille, France is preponed to 1 p.m. instead of 3 p.m. Indian IST. Yeah, I repeat, Dr. Challen's Venkatachalam talk is preponed from 3:30 p.m. to 1 p.m. Thank you all for joining the sessions today. We'll meet tomorrow. Thank you.